I am Alejandro Suárez Mascareño. Where are we? No, that fast. I'm a postdoc at the Instituto de Astrofísica de Canarias, and I'm very happy to be here in this really happy morning session in which we show our shiniest, nicest results so far. And I would like to start by showing you this very nice artist impression of a planetary system. And I like this particularly, not because it's the best or anything like that, but because I did this on an emergency work session at 4 a.m. following a YouTube tutorial. So if you think this is a misleading one, you can just complain to me. I'm the artist this time. And this is an impression of the system of GJ1002, in which we found two temperate Earth mass planets. I will be doing this presentation on behalf of the Espresso Consortium and also a bit as a friend of the Carmenes Consortium, even if I'm not part of that. First of all, GJ1002 is very nearby M6 stars, the best type of stars. And it's really, really close to us and actually really easy to get there. If you wanted to just find a ship there, you just go in the direction of Tau Ceti, take a turn, go through YCZ, and it's just there. We started observing this with Espresso in 2019, but in the Carmenes Consortium, they were observing it since 2016. So combined, we got quite a lot of years of observations. You have here the data of radial velocity and full width half maximum, which was our activity proxy of choice for this case. And for those that might be far away, I promise you the Espresso data has error bars. Well, when I started the analysis of this star, the first thing I needed to worry about was a thing I was not anticipating, and was that there was a parasitic signal in the full width half maximum that seemed to be related with changes in temperature of the shell grating of both Espresso and Carmenes. Now I know this is also in HARPS and HARPS North, and I bet is everywhere. It was fairly easy to correct, and it was not in the radial velocities, which is the thing most people really would be worried about. But in any case, we've had a few comments about how the spectrographs are alive. Yes, they are. Yes, and we just need to listen to them and they will tell us what they are doing. And luckily, it's something that we have measured and we can calibrate for. And in this case, we could. The effect was basically a yearly signal in full width half maximum that could have been mistaken for like a magnetic cycle, something like that. Not the worst case, not something that could be mistaken for an Earth mass planet, but just would advise everyone to be careful. This is something that every spectrograph measures, so we can just look at it. Then, instead of going for the planets, I went for the stellar activity, which is also something I recommend everyone doing. It's a way less stressful process if you look at the activity first. And we measured a rotation period of around 120 days in a full width half maximum of the cross-correlation function of both Espresso and Carmenes. The Espresso one looks really good. Carmenes is a bit more noisy in that case. But I think I didn't say it before, but I would like to point out that this is a B14 star. So it's not easy for a 4-meter telescope, sometimes not even for an 8-meter. And I was very happy to see that the NERPS team, after I published this, published a work on polarimetry on many stars that included this one and confirmed that the rotation period was very long, around 100 days. I was very happy to see that paper. And then what I did was I went for the GP model. We've heard about them a lot, good and bad. And I went for the multi-dimensional GPs, in which we get one underlying GP, and then all the time series are fitted as a linear combination of the GP and the derivative. It works on the same assumptions of the FF' method, that basically you have a flux effect that's created by some spots or something. And then in the velocity, you have the combination of basically the inhibition of blue shift, and a gradient, basically an effect proportional to the gradient of your flux based on basically the geometrical effect of the spots. And I used a combination of two stochastic harmonic oscillators, because after doing many tests, it was the one overfitting the data. We also heard a lot about that, and it's a very complicated issue usually. So first thing was just putting a GP, no planets, just a GP, and I got something like that. And in the residuals, you get 2 peaks at 10 and 21 days. And this is, I would say, a fairly easy case. It's not usually this nice when you just put a GP and nothing else. And then, well, once I got this, we did a model, 1 planet, 2 planets, the usual. I'm going to jump directly to the 2 planet model. That it's a very beautiful one. And it's one that is so nice that you can just see by eye that it just fits the data. It's very, very nice. Even without doing the fit, when we were acquiring the data, we were already seeing the variations. So you can just sometimes choose the model that looks better. But well, we didn't select it because of that. It is significant under a variety of tests. It has a very good Bayesian evidence. And what I'm showing here is basically the kind of periodogram that you get when you apply the optimal detection method, I think it was called, that was presented by Nathan Hara yesterday or 2 days ago, in which it's basically a post-processing of the posterior distribution of the nested sampling modeling that tells you how significant the detection of a planet, of a given period is, depending on the fraction of samples that you're getting there. And a very nice thing of this criterion is that it works even if you get the number of planets wrong. If there are 2 planets in the system and you tell the model, I want 3, it usually will tell you there are 2 if the data is good enough. So after this, we tested that it was basically the same signal both in Carmenes and Espresso, which it's a very good thing because they almost don't overlap. So we are measuring different points in time and they have a different spectral range. And also that the detection was robust, stable in time. In principle, what we expect is that if you have a Keplerian signal, the Keplerian signal does not change. So if you add more data, the detection just gets better, but it's basically the same. There are a few caveats. If your noise changes, these things don't really work all that well. But in this case, it worked really nicely. We found that in our 2-planet model versus no planet, while we were adding more data, we were getting a more significant detection, and that our parameters were pretty stable. So with this, I would say that we did a few other tests, but the main takeaway is that we think we detected 2 planets, 1 Earth mass planets, 1.4 Earth masses. This is the phase folded plot. I think it was in one of the previous slides, but one of the incredible things to me is that the scatter on the Espresso residuals is around 40 centimeters per second. And we are talking about a magnitude 14 star. I didn't think this was possible before analyzing the data, but it shows that both Espresso and the BLT are doing really great, and M6 are great targets for this kind of facilities. And one very nice thing also is that these planets are in the traditional habitable zone. We have equilibrium temperatures of 230 Kelvin and 180, which puts them around there. So GJ1002b would be similar to Earth, kind of, maybe, who knows, but at least it's in a position that's equivalent. And GJ1002c would be somewhere in between Earth and Mars, always under the assumption that you can get a habitable planet there, which I know it's a big assumption. And also, we can maybe in the future characterize them. GJ1002 is so close to us that the sea planet is at 15 milliarc seconds, which is exactly the goal for Andes for the high resolution, high contrast spectroscopy, and to be able to separate it from the star. So for people in the Andes team that might be here, we need to get to that goal. And then in principle, it would be one of the prime targets of the LIFE mission. It falls exactly in the center of the parameter space they want to explore. And then one last time before finishing, we did some detection limits studies with our data, but we didn't, well, there are a few things going on in these detection limits. First, there are two lines. The line below, it's kind of like the traditional detection limit. You have an RMS of the residuals. You do injection recovery, and basically everything below the gray line just cannot be there because cannot be detected with the quality of the data that we have. Anything above the other gray line cannot be there because the RMS of the data will be larger than the one that we measured. And then you got in between a red region and a blue region. The red region is that where we cannot detect things, and the blue region is where we can. How was this done? It was basically the same procedure as for the detection. We have some activity proxy, we train a GP, we go for the velocities, we subtract the proxy and look at the periodogram. And I think the most important, well, there are two messages here. One, it was expected to detect the planets that we expect detected. They are in the blue region comfortably. And then there's a very significant drop in detectability once you get to around half the rotation period of the star. And that's basically the GP fitting everything there is. It doesn't matter if it's planet or activity, as if it were activity. So I think we need to do better if we want to detect a planet at 10 times the rotation period of a star with a signal that's smaller than the rotation signal. And with this, I will leave my conclusions and I'm done. Thank you.
We have time for a question.
Very nice work. So does that work with a straightforward GP analysis? So you really need the multi-dimensional one to get the signal
out? For this, do you mean? Well, for this, it's what a bit more straightforward. I didn't do the MCMC for the, because this is like 100,000 tests for the grid. I couldn't do the nested sampling with the simultaneous fitting for all of them. So maybe we can do better if we do put like all the big guns. This was in a more naive approach. I trained on the activity, I subtracted from the velocity, I looked at the residuals.